Let's review that tutorial that we had this week. When a pulse comes into a boundary between two media, a slow media and a fast medium, it splits, and some of the pulse goes through to the new medium, and some of it bounces back as a reflected pulse. Now, let's just agree up front that doesn't seem that important when you're dealing with one spring connected to another spring. I mean, how many times in your life have you had two springs connected together and sent a pulse and worried about what happened at the boundary? Not so much. But this phenomena happens all over in our everyday life. If you're setting up a stereo system, you want the impedance of one part of your stereo system to match the impedance of the others. And if you don't, if there's a mismatch, then the signal coming in is going to split. Some of it's going to reflect back and some will transmit in. If you have water and it's going from a region where it's deep to a place where it's shallow, if there's a cliff underwater, what you'll see is that the wave will come in, and right at the boundary it will split. And some of the wave will go forward and some will bounce back. It's just everywhere in nature, if you've got a fast and a slow region brought together, you get this dividing. Now, here I have represented two springs. They're tied together. One of them's fast and one of them's slow. I had a pulse, an incident pulse, come in, hit the boundary and split. After that pulse split, I took this picture. Can you tell which spring is the fast one and which one's the slow one? Okay, the fast one's on the left. Now here's how you tell. One way to think of this process is that the incident pulse, the original pulse, I call the mother pulse. Okay? The mother pulse comes in and gives birth to twins. And in the process, unfortunately, dies. But the twins take off in both directions. Now, these are the twins. Those twins were born at midnight at that hospital right there, both of them. Okay? And they scurried off. And you can see that that twin got further away from the hospital than this one in the time between when they were born and when I took the picture. Okay? So that's going to be the fast spring, that's going to be the slow spring. Now, if I had these two springs, where this is a fat spring and this is a light spring, which of those would be the fast and which would be the slow? Yeah, the light one would be the fast one. Your gut tells you that. Now we can argue that either from an equation or from our common sense. If we use the equation for a pulse speed on a transverse medium, like a spring, it's going to be the tension divided by the mass density. Now these two springs are pulling on each other. Can the right one pull on the left one harder than the left one pulls back on the right one?
No.
No, it would violate Newton's third law and then the universe would end. Okay? That's the most beautiful of all laws. And so whichever spring has the biggest mass density is going to have the smallest speed. Now another way of thinking of this is intuitively. If you think of these pulses passing from neighbor to neighbor, think of the heavy spring as a whole bunch of football players, the linemen standing up here. And we got to pass the pulse by lifting up our neighbor. Oh man, you're big. And then the other spring is made up of ballerinas. Okay? And it just goes really fast. Okay. Now, say I have a pulse like that coming in on the slow, and it hits that boundary. Will the transmitted pulse be on the same side or the opposite side in this case? Same. Is it the same side in this case, or is it the same side in every case? Every case, every stinking time. You never have to worry about that transmitted pulse. It will always be on the same side as the mother pulse that created it. Okay? Now, what about the width? Is it going to be the same width as the original pulse, or wider or narrower? Wider. Okay? The question is, why? Now, the second page of that tutorial dealt with the why. You represented a pulse by two pulses. One pulse that was at the beginning of the original pulse, one that was at the end. And you figured out why it had to stretch. I'm going to do it a different way here. I'm going to represent that pulse as a school bus. But not any school bus. This is a magic school bus. This school bus can stretch, it can shrink, it can be whatever length it needs to be. And it's driving on a really, really slow road, a dirt road that's all bumpy. And it gets to a boundary with a fast road of pavement. Now when it gets to that boundary, the front of the bus speeds up. But the back of the bus is still back there in the dirt, going slow. And so sure enough, it stretches out. Okay? Now if it's going the other way, the front of the bus hits the slow side first and slows down, and then you have the pulse shrinking. Okay. So it's going to be wider. Now folks, don't worry about the amplitude. The amplitude, how high it is above equilibrium, that's messy, that's challenging. Sometimes it's bigger than the original, sometimes it's smaller. All you can really say for sure about amplitude is the reflected that's on the same spring as the incident will always have a slightly smaller amplitude. But we'll never test you on amplitude, just width. Now, consider the reflected pulse. Is it going to come back on the same side or the opposite side in this case? The same side. Because when you're going from a heavy to a light, that's acting like a free end. And we found last week that a free end reflects back on the same side. Now if we came in on the light and hit the heavy, that would be like hitting a fixed end, and then it would invert. Okay, one more question. If that comes in like that, the reflected pulse has to be on the same side, meaning up, but which way will it be oriented? Like this or like that? This or that? Like that. And the reason is the leading edge has to lead. Okay, the leading edge is the first part that hits the boundary, turns around and goes the other way. Okay, the leading edge always leads.